Okay, so in this video clip, we will take a look at how uh, parameter sensitivity actually represents a foundation for understanding the Black-Scholes-Merton Greeks. So essentially, when we talk about parameter sensitivity, we're looking at the extent to which a change in the underlying set of input parameters has an impact on the value of the option. So for instance, if the value of the stock goes up, we know for the Black-Scholes model, the value of the European coal goes up based on the model and the logic of um, how options are priced. Likewise, there's a negative relationship between the European coal and the strike. For time to maturity, it's not clear. In fact, there are situations where as the time to expiration increases, the value of the option drops down. Most of the time, as you increase the time to maturity or expiration, the value of the option goes up, but there are exceptions, so that's why it's indeterminate. And the volatility, in every case, when volatility increases, we observe an increase in the value of the option. Likewise, for the risk-free rate, as it increases, it tends to have, if you can imagine for a moment the Black-Scholes formula, the effect of increasing R depresses the value of the exercise in the overall call. So thus an increase in the value of the interest rate tends to increase, unambiguously increases the value of the call, and then dividends the reverse relationship. Now we can observe those directly. And if you want to delve a little bit deeper into option properties, there's an excellent chapter in John C. Hall, um, chapter 11 on the 11th edition. I leave the links here and I'll share this collab with you directly underneath the video clip that I'll post. Okay, so this is basically a preamble to understanding the logic behind the Greeks and the idea that we would like to calibrate. So, although we can observe directionally the effect of changing any of the parameters, what the Greeks do in effect is put calibrate that, but make the magnitudes clearer and explicit. Okay. So again, a little bit of an overview of the different parameter inputs for the Black-Scholes model, and maybe just for reference, Black-Scholes model, um, for reference, in the same collab, you will be able to take a look more closely at the Black-Scholes model here for the call and for the put. Now going down to parameter sensitivity for the option, if we were trying to observe the impact of changing each of the parameters in terms of the value of the option, we could run this snippet of code. And essentially, I've isolated, if you like, the Black-Scholes call model, and we're going to interrogate that model in terms of changing each of the parameters and observing directly the effect of that on the value of the option. So initially here, in terms of our library, we bring in NumPy for as it's a mathematical library, some statistical functions from SciPy stats, and Matplotlib for graphing. Then we set out a range of parameters where we take, in each instance, we select a parameter that we lock, and then we allow in each instance each of the parameters to vary sequentially in the range for the stock price 50 to 200 at steps of 5. Likewise for the exercise, the time to maturity 0.1 to 3, button 50 steps, and Q also 0 to 10%. Plausible amount of dividend would be up to 10% in 50 steps, and sigma 5% to 60 in 50 steps, and then going from 1% to 15% for the R in 50 steps for the interest rate. Okay, so when we run our snippet of code here, we're basically taking each of the parameters. So we're observing the effect on the Black-Scholes call valuation by changing the stock price. So we lock all the parameters except for the stock price, and then we allow that to change sequentially, and we can observe the effect here going from 50 to 200. And we can see here as we increase the value of the underlying, the value of the call option goes up. So that's consistent with our table that we have here. As we increase the stock price, the value of the call goes up. As we increase the strike price, the value of the call goes down. As we increase the strike price, the value of the call goes down. That's a negative relationship. And then for the maturity, it would appear here at first glance, as we increase the maturity, the value of the option goes up. As we reduce the maturity, the value of the option goes down. That sounds plausible, but it doesn't seem consistent with the table here because it says it's indeterminate. And to understand why that there may be exceptions here, if we changed the dividend from 0 to 10%, right, and observe here specifically this chart. Let's rerun our series of tables, graphs. We notice here that there are instances that as we increase the maturity, the value of the option actually drops. So there are instances where we observe a breach. We can accentuate that again if I take a higher dividend yield and maybe implausibly high dividend yield and run again, we have a more dramatic effect. You can see that there are situations that as the dividend yield is high, then as we increase the maturity, the value of the call option can actually drop. And that's why we're getting that indeterminate relationship in terms of time to expiration and the value of the call option. It's not clear. There are circumstances where as we increase the maturity of the option, there are some instances where the value of the call can drop. Likewise for the put, which I don't demonstrate here, but we could if we changed our code, if we introduced here BSM put and returned the value of the put option based on Black-Scholes, and then sequentially came down here and input it in for the BSM put, right? But I haven't done that just for brevity. Now I'll go back and change the value of the dividend back to 0. And some companies don't pay dividend, like Amazon, I think historically haven't paid dividend. So normally, yes, as might be expected, as we increase the maturity, the value of the call option goes up, but there are exceptions. Again, the sensitivity of the value of the option to dividend, it would appear here as we increase the dividend, the value of the call drops. As we reduce the dividend, the value of the call goes up. So that's a negative relationship. And then the volatility is fairly clear cut. As we increase the volatility, the value to call option goes up. So it's a positive relationship for volatility, a negative relationship with dividend yield with respect to the valuation. So the value of the call with respect to Q here would appear negative. And then for the risk-free rate, if we increase the risk-free rate, it would appear the value of the option for the call option increases. Okay, now what the Greeks do by extension is they provide us with, in each instance, the level of change with respect to the underlying or with respect to the exercise. It can vary substantially. So for instance, here, when we increase the stock price, the value of the option goes up very little. but up here, an increase in the value of the underlying increases the value of the option almost 1-for-1. Down here, it's 0. So the slope of the Black-Scholes parabola actually gives us a measure of the sensitivity, but that actually is dependent on what the underlying asset price is. And the other parameters influence this. So for instance, if we isolate purely this table, this graph, and rerun the same exercise again, but in this instance, we're going to consider different levels of volatility, 20, 40, and 60%. We can see that the sensitivity of the parabola actually changes as we increase the volatility. So while we can discuss generally parameter sensitivity and eyeball it, for more precise calibration of that sensitivity, we used Greeks, which would be the delta, gamma, vega, theta, and rho. And that's why we typically see in many of the trading platforms references to the Greeks. So even if we go to, for instance, Schwab, here you will see for even on the retail side, there are there's material relating to explaining to investors the delta, the theta, the gamma, vega, and rho, right? And they go into quite a bit of detail around that. Okay, going back to our parameter sensitivity and coming down to our chart here that maps out the relationship between the call and the value of the call and the value stock price and the value of the call, we can see it's actually quite interdependent on volatility as well. And the Greeks served to give us a finer, more granular estimate, not just directional, but actually the magnitude of that sensitivity. And so it's always worthwhile when we discuss the Greeks to frame it in terms of the parameter sensitivities. The sensitivity of the option to changes in the parameter inputs into the model. For a more generic overview, right, I'm going to rerun the first graph again, but I'm going to look at 3 different levels of volatility. And again, this graph here is the same as the first one that appears here. And we can see, in fact, as we increase the volatility from 10, 20 to 40%, the sensitivity and the slope of the Black-Scholes parabola also changes. So here, with the higher level of volatility, the value of the delta, the slope parameter, is higher much earlier where the option is out of the money. So it elevates all the values here in the out of the money for the delta on the call option. But all converge to a 1-for-1 relationship approximately. The maximum value in delta is typically 1, right? So they all converge 1-for-1. But here you can see, while very little sensitivity for the low volatility option, as the volatility goes up, the sensitivity is much more dramatic with the out of the money call option. Again, we observe something similar here in terms of changing the value of the exercise with respect, changing the value of the exercise with respect to the option. Its impact on the option is much more dramatic for the higher volatility. Now, we don't typically have a Greek. The delta refers to the change in the value of the option with respect to a change in the value of the stock. Gamma is the second derivative. It's the change in the value of delta with respect to the change in the value of the underlying. And then typically we look at the maturity, but it's the lowercase t, it's the time decay. So we kind of put the relationship in reverse. Typically, as we increase the maturity, the volatility option goes up, but as time drops, the volatility option goes down. So with an increase in time decay, which is sort of a reduction, dropping the remaining time left on the option, we see a drop in the value. So a lot of the time, theta is negative. And again, I can perform that experiment and observe directly what's the effect if I increase the dividend yield to 15% and lock it then. You can see for the the effect of increasing the maturity in the option is to reduce the value, especially for deep in the money options, right? Uh, we would have that would be more acute, right? That would be so if we change, uh, how would we do that? I could come back here to, let's say, change for deep in the money option. I'll go 120 and now observe the effect. Right? So you can see in sharp contrast how that dramatically changing, and the dividend doesn't have to be as elevated, even with a dividend of perhaps 5%. And run that again. You can see if we come down, for the lower volatility, it's dropping. For the higher volatility, it's going up, and for the higher volatility, still rising. But if we increase the dividend to back to the 15%, you can see that in each instance, then as we increase, and again, this is for a higher, so the stock price is higher than the exercise or deep, reasonably deep, and in the money option, as we increase the maturity to value, the option drops. Again, that really is the observed here in this table. It's indeterminate, the effect of changing the value of the maturity on the option value. Because if dividend is high and the option is deep in the money, the value of the option can actually drop as we increase time to maturity. In other words, a positive theta occurring. Normally, theta is negative, but with a dividend, theta can be positive, and we'll observe that later on. So again, for framing the analysis and observing the relationship between the parameters and the value of the option, we first of all could manually estimate the impact and graph that in terms of the value of the call and the put, where we considered the three level of volatilities. Again, where the volatility tends to be higher, the green here, the 40%, the change of dividend and the change of the interest rate is much more dramatic for the lower volatility. Again, how do we combine all those elements together to give a single metric that explains what's going on in terms of the option? We introduce the Greeks, the delta, the gamma, the vega, theta, and rho. And I'll leave those definitions here just below the video clip, and you'll be able to pick up on later. Okay, let's leave it there.